Hey there! Here we go into the next chapter. This is all about area, volume, and arc length, this entire chapter. And we're going to start out first with finding the area of a region, or a bounded region. And what this is all about is actually finding the geometric area. So even if area happens below the x-axis, it's still positive. We're talking about how much paint can I cover a surface with here. So what is the geometric area? And we're going to start out with a problem that we've actually done something like before. And so it's important when you graph these things out, when you're asked to graph out a region, that you remember that you don't actually have to be super accurate. You just have to get a rough picture, unless your teacher's saying, hey, give me an accurate picture. So I'm going to do rough sketches. So this says, find the area of the region bounded by y equals root x, y equals 0, x equals 0, and x equals 9. It's important we practice how to find what that region is. Start out with this curve, y equals root x, and that's just something like this, just a rough sketch, right? So there's root x. Y equals 0 is the horizontal line here, or in other words, known as the x-axis. I'm going to do that in a different color. And so that would be this right here. So that's one of the other parts that bounds the region, right? We're basically enclosing the area. X equals 0. That's a fancy pants way of saying the y-axis right here. So we know that we're somewhere in the first quadrant, and it's either up here or down here, and x equals 9. Okay, well, x equals 9 is a vertical line here. So what bounds the area? X equals 9, root x, y equals 0, x equals 0. That would be this space right in here. So we're looking at that area. So the question becomes, how do we find that area? What I like to do on every single one of these problems is remind myself of the concept of how to find the area of a region. And so what I always do is I draw in what I call a representative rectangle, or is what I affectionately call reprect. Okay, so with this representative rectangle, I'm going to take that out and we're going to look at the big representative rectangle here. And remember that this width right here is dx. It's a very, very small change in x. And what's the area of a rectangle? Well, the area of a rectangle, glad you asked, is base times height, right? Well, the base is dx and the height is whatever this is right here. So I'm going to switch that up. So that's going to be dx times the height. So that's dx times whatever the height is. Well, the height is going to be this distance, or the distance from the upper curve down to the lower curve. Because we're looking at geometry here, you want to keep things positive. How do we do that? You always have to do the upper curve minus the lower, or top minus bottom. So we're looking at that as the height. And if you think about it, the reason why we subtract is whatever this y value is minus whatever that y value is, we are going to get the height. So if I put the rectangle here, whatever that y value is minus this y value, we get the height of the rectangle. So what's this upper y value? Well, that is dictated by root x. So I'm going to put that here. And what's the lower y value? That's y equals 0. Imagine a rectangle sliding along like that. And so that's going to be 0. So overall, the height is going to be root x minus 0. And I sometimes use what I call the caveman or cavewoman technique, which is I first point at the curve and say, ugh, minus ugh, so that I don't involve my algebra until I've pointed out what I'm subtracting. This minus that, root x minus 0. Okay, so now the area of my rectangle is root x times dx. And you might be like, yeah, where's the integral here? Don't we have to integrate to find the area? Sure we do. All I'm going over here is the area of one tiny rectangle first. Okay, so now, from here, we want to add up infinitely many of these super tiny rectangles, sliding them from left to right. How do I add up infinitely many rectangles? Well, I'm going to add them infinitely many times. So I now take the integral of root x dx. And the question is, from what x value to what other x value will I stack up these rectangles? Well, we have x equals 0 to x equals 9. And that right there is the most important part. And I wrote a note down here, set up but don't evaluate in your practice. So if you're practicing 5 problems, you set this one up and then you go on to the next one and set up the next one. Don't integrate it. Go back and integrate them all together. That way you're practicing going from graphing to finding this proper integral that gives you the area of the region. Then you can go and integrate it. Because I'm giving you the full lesson here, I'm going to go ahead and integrate it. But this is it. That's the new part. And really, it's kind of old stuff. Okay, so from here, I'm going to integrate. This is all old school now. The integral of root x. Remember, that's x to the 1/2. That's x to the 3/2. Divide by 3/2 is the same as multiplying by 2/3. And we integrate, or evaluate that from 0 to 9. And so that's going to be 2/3 times 9 to the 3/2. Very nice. Minus 2/3 times 0 to the 3/2. It's using the first fundamental theorem. 9 to the 3 halves is 3. Cubed is 27. Times 2 is 54 thirds. And that's my final answer. This is just 0 here. All right, before we close out this video, I want to go over, generally speaking, how you find the area between two curves. Technically, we found the area between root x and y equals x. So how do we do this in general? Well, let's say that you're given two curves, the orange curve being g of x, and the blue curve, I think that's blue, I'm colorblind, so we'll call it blue, is f of x. And we're doing that from A to B. That's the region, so we're looking at this region right in here. What I always do, again, is I draw in a representative rectangle, anywhere, just to understand this. And that rectangle, well, the area, remember, is length times width or base times height, however you want to look at it. The area is going to be this thin width here of dx multiplied by that height. And that height is always going to be the upper curve minus the lower curve, again, because you want to keep your dimensions positive since we're finding geometric area. Well, in this case, the upper curve is f of x, so that's f, minus the lower curve, which is g. And no matter where you put the rectangle, that's the case here, right? We just got one single region where f is the upper curve and g is the lower curve. We'll talk later on in a different video what happens when we have g and f kind of switch from up to down and down to up, meaning what the top and bottom curves are. So that's it. And then you integrate that because you want to add up infinitely many rectangles. So we'll call that f of x minus g of x, top minus bottom, times d of x, and we're going to integrate from A to B, or top minus bottom dx. So you could also write it like that, top curve minus bottom curve. All right, that's all. Couple of key factors. Always lead with your geometry. Always think about the geometry first. The calculus is actually just the idea of adding up infinitely many of those rectangles because we need so many tiny rectangles to fill up the space perfectly. The geometry is actually not bad. It's the height of a rectangle, the width of a rectangle multiplied together, and we want to keep things positive, so top minus bottom. See you in the next video. Peace.